In the last episode, we saw how ground-penetrating radar grew from the theories of James Clerk Maxwell to the spark-gap experiments of Heinrich Hertz into a powerful tool for looking beneath the ground. Today, we're going to be peeling back the science behind GPR, how it really works. Now don't worry, we're keeping this as clear and friendly as possible. I'm aiming it for about a grade 12 physics level. So we'll look at how radar electronics generate pulses, how antennas launch these pulses into the ground, and how the waves reflect off different materials in the ground, and why the key to it all comes down to one thing, something called dielectric properties, which in practice mostly means moisture. By the end of it, you'll understand how radar transforms invisible ripples of energy into images that reveal the hidden world below our feet. At its core, a radar system is just an electronic echo machine. It sends out an EM pulse, electromagnetic pulse, a quick flash of radio energy, and then listens to the echoes that bounce back, and it measures the travel time. A GPR does the exact same thing, except it sends its pulses downwards into the ground. So let's start with how that pulse is made. Inside a GPR transmitter unit, an electronic circuit charges up like a series of capacitors. Then, in an instant, it releases that energy as very short electrical pulses, often a few billionths of a second long. That's what we call an impulse-type GPR system. Now, because the pulse is so short, it contains a very broad range of frequencies, a bit like how a camera flash contains many colors of light. Now, these different frequencies let the radar see different details in the ground. After generating the pulse, the radar sends it into an antenna, the bridge between the electronics and the physical world. That antenna converts that tiny electrical signal into an EM wave that travels outwards at nearly the speed of light. Now, for most GPRs, you usually have two antennas, one for transmitting and one for receiving. This is called a bistatic radar. The transmitter launches the pulse into the ground, and the receiver listens for the echoes. So, how do antennas actually send out electromagnetic waves? Well, think of electrons, those tiny charged particles in a wire. When you push them back and forth, they create changing electric and magnetic fields. Those changing fields ripple away as electromagnetic waves. In a GPR antenna, a very quick pulse of high voltage into a conductor creates a fast current pulse, which makes the electrons surge and stop almost instantaneously. That sudden motion launches the electromagnetic ripple outwards. You can picture it like a snapping of a rope. The sharp motion at one end sends a wave racing along the rope. And the same thing happens with electrons in the antenna, except the wave travels through air, soil, or rock instead of a rope. Now, different antennas are tuned to different frequency ranges, so a large antenna launches longer waves that go deeper but show less detail. A small antenna launches shorter waves that reveal finer detail, but they don't go very deep. And that's why no single antenna can do everything. It's a balance between penetration and resolution. We'll come back to that idea later in the series. Once that radar pulse leaves the antenna, it travels down into the ground, but not very far before it starts interacting with materials in the ground. Now, to understand what happens, we need to talk about something called the dielectric constant. It's a measure of how easily a material can be polarized by an electric field, or in simpler terms, how much the material resists or slows down electromagnetic waves. Now, air is the fastest. It has a dielectric constant of 1. Dry sand is about 3. Wet soil can be 15 to 20. And water, the wettest material, of course, is about 80. Now, metals are an unusual dielectric because essentially they have infinite dielectric. And that's why both the dielectric constant and the electrical conductivity control how radar behaves underground. More moisture usually raises the dielectric constant, so slowing the wave and strengthening reflections at boundaries, but it also raises conductivity, especially in clays or salty water, which absorbs the radar energy and limits depth. Now, in clean, dry materials like quartz, sand, or glacial ice, which is very, very low loss, waves can travel many, many meters, sometimes tens or hundreds of meters at lower frequencies. Conversely, in wet clays, saline solids, seawater, the energy is damped very quickly and may die out within tens of centimeters, even if the dielectric constant is large. So permittivity changes, and by that I mean moisture changes really, create reflections, and conductivity changes limit penetration. Just because there is water presence doesn't mean that penetration will be severely limited, unless it is water which contains minerals, which will make it then conductive. When a pulse hits a boundary between two materials with different dielectrics, so different moisture, say dry soil and a buried pipe, or dry soil and wet soil, part of that energy reflects upwards and part of it continues downwards. The GPR receiver listens to those backwards reflections. By measuring how long they take to return, it can calculate the depth of each layer or each object. Now, each reflection's strength also tells us some information. It tells us how big the change in dielectric was. And each reflection's time delay tells us, well, how far away it was or how deep it was in this case. Metal objects are special because their dielectric is effectively infinity. Their reflectivity is 100%. So almost all the energy produces bright, bright reflections and very sharp echoes. Moisture variations, on the other hand, cause weaker but still visible reflections. So that's why GPR is great for detecting pipes or rebar and also mapping layers of soil or concrete, because each boundary has a different dielectric signature, that is, a different moisture. Now, let's connect this all together. The radar sends very short pulses of voltage into antennas, and it does that hundreds of thousands of times per second as it moves along the ground. Each pulse produces echoes from different depths as it leaves the antenna. The GPR records these echoes over time, forming a continuous image, a radargram. When plotted side by side, these traces, individual traces, reveal curves called hyperbolas, each making an object below. Flat reflections show layers, curved ones show buried object. It's like sonar for the ground, but using radio waves instead of sound. It's important to understand radar doesn't produce an image of an object directly. It records the way the wave responds. What we interpret visually are patterns in reflection time and strength, and that's what makes GPR both a science and a lot of art. So let's recap the main ideas behind how GPR works. The transmitter electronics generate a short, very powerful pulse, little electromagnetic flashes, if you will. The antennas convert those pulses, those flashes, into waves that travel into the ground. The waves reflect wherever there is a dielectric constant change, usually where moisture changes, even slightly. Metals reflect everything. Moist soils absorb waves very quickly, dry sands let waves pass further. The radar listens for echoes and measures how long they took to return, building up an image of the subsurface. So I guess next time you see or you use a GPR device, you see it on TV, remember, it's not just seeing underground the way your eyes see it. It's listening to this symphony of echoes, turning invisible radio ripples into a picture of what lies beneath our feet. Thank you very much for listening. I look forward to showing you the next episode.